I hope you enjoyed my dreams. I did not intend them to be solely taken as stories. They do actually represent my current view on reality. Though I do want to know if my view of reality is true or not. I've thought of 2 experiments, one of which could be done or begun today, and another which could be completed in 10 years. The results of these 2 experiments would either be extremely surprising to the conventional view or lend support to my view of reality. The first experiment, which could be begun today, would observe as its final result that dark matter appears to break Newton's law of universal gravitation. Newton's law of universal gravitation states that for any 2 bodies in space, they will, through the act of gravitation, exert on each other an equivalent force. Meaning, if the 2 bodies have the same mass, they will both accelerate towards each other at the same rate. Now, if you remember, I said dark matter is not actually any matter present within our universe. It is a gravitational wave depression created by objects moving outside of our black hole universe event horizon. So these gravitational field anomalies, which we call dark matter currently, will disobey Newton's law of universal gravitation, meaning if we're able to identify a focus of dark matter and estimate its apparent mass by the gravitational lensing it creates, and observe a nearby focus of conventional matter, what I propose is that we will see the conventional matter accelerating towards the dark matter, but the dark matter's trajectory unperturbed by the presence of conventional matter. That's because dark matter is a gravitational field caused by a very large object outside of our event horizon. And the effect of a mass within our black hole universe on a much larger and more massive object outside of our black hole universe is negligible. Therefore, the gravitational field, which we call dark matter, will move in a way which shows complete disregard for other foci of dark matter and conventional matter. The second experiment we're going to build to, and I believe this experiment could be completed in 10 years when we have at least 3 laser interferometer gravitational wave observatories, LIGO detectors. A LIGO detector allows you to detect gravitational waves which have emanated from a cataclysmic, distant, celestial event, such as the merger of 2 large black holes. The merger of 2 large black holes releases gravitational waves which can be detected by LIGO. The merger of 2 large black holes also releases electromagnetic radiation which can be detected as photons by observatories on Earth. The map of the universe which we currently possess is based on the paths of photons. Meaning we know if we point a telescope in a certain direction and focus on at a certain distance, at a certain time, we will see a certain object. Because we have mapped, to a reasonable degree, our universe. We know where objects are, where we have to point our telescope if we want to find them. But that map is built entirely on the path that photons take through space and time, and we know that photons take a curved path through a space-time field with a gradient, or a heterogeneous space-time field. Let's take a hypothetical space-time field, and I'll show you what I mean by this curved trajectory. Say we have an observer on the planet Earth and an event which is some 100 million light years away. In order to observe that event so very far away, we point our telescopes in this direction. We might assume that this is actually where the event occurs, but the fact is the event is here, and the photons took a curved path to arrive into a telescope which was pointed in this direction. The map of the universe we have built is based upon the predictable and reproducible curved light paths of photons through space-time. Now, if you remember, in order for the gravitational field of objects outside of our black hole universe event horizon to penetrate to the inside and be interpreted herein as dark matter, I suggested that gravitons can cross the event horizon, whereas photons can't, and this was because they follow different paths through a space-time field. I'm going to suggest that we can reveal this different path with 3 LIGO detectors, and we can create a gravitational map of the universe which will be different than the photonic map of the universe that we currently possess. I do not know the exact path that gravitons will take. Photons are generally accepted to take the least time path. I propose, though it may not be true, that the different path gravitons take may be the least distance path. And I do believe current evidence shows that for any observer observing an event, both the photons and the gravitons arrive at the same time. And I believe this will also be true as more evidence accumulates, which suggests that a graviton has variable speed. But first, the discrepant event triangulation. With our telescopes, we've built a certain map of the universe, saying we point our telescope here to observe that event. Now, in order to observe, so if we use, say there was a black hole merger that occurred right here, and it released a large burst of electromagnetic radiation, which we detected in our conventional telescopes on Earth. Our telescopes would be pointed in this direction and would say this is where it came from. But I'm going to suggest that the gravitons take a different path. And our LIGO detectors for that same event will point directly to the event. And this will cause us to suggest that by graviton triangulation, the event occurred in one location, but from photon triangulation, the event occurred in another location. This discrepant event triangulation would support my claim that gravitons follow a different geodesic than photons. I believe the curvature of this photon path, which will become apparent when we see the straight line path of the gravitons, I believe this curvature will be extremely revealing about the nature of our universe. Seeing me draw the photon path in this way, you may ask just as well, why doesn't the photon path curve this way? Let's talk about this. Let's imagine a sphere that has a uniform mass density. For all intents and purposes, we could take the Earth as an example. It is near enough to a uniform mass density to illustrate my example. Say you dug a hole through the center of the Earth and you jumped in. Where would you end up? Well, you would yo-yo back and forth and end up in the middle, essentially feeling weightless, like you're floating. Now here's a different question for you. Where in this sphere with a uniform mass density is the gravitational field the greatest? Meaning, where is space-time dilated the most? The answer is here, in the center. Though you are weightless, the gravitational field is most intense in the center of a sphere with uniform mass density. Space-time is most curved in the center. If you were in the center and had a stopwatch, and you had a friend on the surface with a stopwatch, you let them run for some period of time, starting them simultaneously, and then you came back together, either in the center or on the surface, you would find the stopwatch, which had been in the center, had elapsed fewer seconds than the stopwatch on the surface. So, in a spherical mass with a uniform mass density, there are concentric rings of gravitational field. Each ring, as you pass towards the outside, the gravitational field is less intense. We had been talking about the planet Earth. Now we can talk about our universe, our black hole universe, which is a sphere of approximately uniform mass density. There is a center to our universe, and in the center, the gravitational field is the greatest. There are concentric rings of gravitational field surrounding that center. The curvature that the photons take will suggest the direction of the center of our universe.